Before we can understand how linear algebra can be used to represent music, we need to have a baseline understanding of music theory.
Don't be scared of music theory. There are just a few definitions you will need to be able to follow along. And of course, rewind or pause this video if you need any extra clarification.
We're going to use the instrument that most clearly lays out music theory to understand these concepts, the piano.
A standard piano has 88 keys and yet only 12 distinct pitches. Each group of 12 makes an octave, and this is what all the notes in one octave sound like.
Then it restarts because those 12 notes are the same.
When we play all of the notes in an octave, this is called a chromatic scale. Each note is a half step apart.
A half step and an octave are both examples of intervals. That is the distance between two notes. It is also the ratio of their frequencies.
An octave, for example, has a 2-1 ratio. A fifth has a 3-2 ratio. Generally, the simpler ratio, the more simple the sound. The octave is generally much nicer than this, a tritone, but don't worry too much about the ratios behind frequency.
Yeah, just remember that some notes, called consonant, sound nice together. Others don't sound nice together. That's called dissonance. This is where the idea of scales and keys and grouping these notes together comes in.
A key is a collection of 8 notes out of the 12-note octave that essentially sound good together. This is because they are certain intervals apart.
A key also has a set of chords that belongs to it, made up of multiple notes at a time that all belong to the key. So for example, the scale you just heard, the chords that belong to that key would be
Now, what does all this have to do with linear algebra? Well, all of these 12 notes in an octave can be represented through a 1/12 matrix, where each entry in the matrix corresponds to a note, a 1 if the note is played, and 0 if not. We will start our matrix with C as the first element, then progressing, like the keys in a piano, to C sharp, D, D sharp, and so on, to have the other 11 elements' places. So here, this is a matrix for C. We only have the 1 in the first spot and a 0 in all the other spots because we only are playing for C. On the other hand, a key does not have every note in the chromatic scale. So a matrix of this key's scale, which is the C major scale, would look like this. You can see that there are 1s in the places of each natural note, so C, D, E, F, G, A, and then B, while there are 0s in the places of each sharp or flat. This makes sense since the C major scale is only made up of the natural notes, which correspond to the white keys on a piano, and does not have any sharps or flats, which correspond to the black keys. So a matrix for the C major scale would look like this. As you can see, 1s in the places of all the natural notes and 0s in the places of all the flats or sharps. It's kind of like a binary system. We're only using 0s and 1s, where 0 means the note is not being played and 1 means the note is being played.
Diatonic music and matrix operations. Now that we've established a method for capturing musical notes in a matrix, we can use matrix operations to learn more about the music we're playing. Say we want to learn if a specific set of notes is in a given key. From a music theory lens, this would be true if all of the given notes were in the set of notes in the key. As for the matrix representation, we want to line up the two 1/12 matrices and compare which columns have zeros in them. We are checking if there are any non-zero values in the note matrix that correspond to zeros in the key matrix. Thus, we can see that this specific note matrix does not fit within the key. Now, is there a more mathematically rigorous way of computing this? Well, let's start with the simple case in which none of the notes are in the key. To check if this notes matrix belongs to the key matrix, we can take the dot product of the two matrices. The dot product will be 0 if the note matrix and the key matrix have no notes in common. This is very similar to the concept of AND in Boolean algebra. Let's try an example. The dot product of this notes matrix and key matrix is 0, which means that they have no notes in common. So this set of notes is not in the key.
But what if there are some notes in common? The dot product would be non-zero, but the note matrix still may not be completely in the key matrix. A more rigorous test would require individually multiplying each set of corresponding elements without summing them up. This can be accomplished with element-wise multiplication, also known as the Hadamard product. You can see that for a given element aij, it's multiplied with its corresponding element aij hat in this formula below. Let's first do a simple example with matrices we're used to seeing. We'll find the Hadamard product of the matrix 2, 3, 4 with the matrix 1, negative 1, 2. So we know that the product matrix will have the same size as each of the starting matrices, which is 1 by 3. So we can start by doing out each of the individual element-wise multiplications. So that will be 2 times 1, 3 times negative 1, and 4 times 2. Now we can do out the multiplications to yield 2, negative 3, and 8. So the element-wise product of 2, 3, 4 and 1, negative 1, 2 is equal to 2, negative 3, 8. Now, following the same principles from our dot product test, if the Hadamard product preserves the note matrix, then it must belong to the key matrix. In other words, if and only if the note matrix times the key matrix using element-wise multiplication is equal to the note matrix, then all of the notes belong in the key. Let's do an example to test this out. How about the matrix that we started off with? So we've got the note matrix here and the key matrix. So this will yield another 1 by 12 matrix, and we can do at the multiplication. And then we do out the multiplication to yield . And we can see here that this is different than the original note matrix in this fourth element here, indicating that the note matrix does not belong in the key matrix. However, if this singular element had been switched from a 1 to a 0, then you could see that the matrix would otherwise be intact, and that would be in the key matrix.
So now we can see how this works with real music. So we can take something that's really easy, which is the 12-bar blues. That just uses 3 chords. The 1 chord, which you can represent with the 1 chord matrix that we've already learned. The 4 chord, we can represent that with the 4 chord matrix we've already learned. And then the 5 chord, same goes for that. We've already learned how to make those matrices. And so we can imagine a whole blues song, which is just built off using these 3 chords, 1, 2, 3, as just repeating those matrices over and over again. So a 12-bar blues progression, which is the foundation of so much music, including a lot of rock and jazz music, is just this. 1 chord matrix. 4 chord matrix. 5 chord matrix. 4 chord matrix. 1. So now you can use the matrices that we've made, put them in order, and you generate essentially a song matrix. And if you row reduce that matrix, you can find that the only linearly independent rows are going to be the individual chords that you use, 1, 4, and 5. So now we've gone from saying I can list notes in an order to figure out what chord it is, to saying by knowing which chord it is and how the chords are related to one another, I can pick that something's in a certain genre of music. So when I row reduce and find that I'm using these three chords, the 1, 4, 5, I know that I'm in fact playing a blues.
Now, forget everything you just knew about how to analyze music through a diatonic within a key. We're moving on to serial music, also known as 12-tone composition. So forget the idea of keys. In 12-tone music, every note from the chromatic scale is of equal importance. Once you've used a note, you can't repeat it until all others have been played. The idea of this serial atonal music was developed in the 1920s by composers like Arnold Schoenberg and is possibly the most obviously mathematical form of musical composition. So let's look at how this composition works. A composer would take all the notes from that chromatic scale and put them in a random order into something called a tone row. So after making this original ordering of the 12 notes, which might look something like this in a matrix, composers can then perform a number of changes to alter that sequence while still obeying the main rules of serial music. This would be an example of our starting matrix, where we have a 1x12 matrix that each represents the order in which these notes are going to be played. So for example, a 7 corresponds to an E because we're starting with the A, and we go straight on and make sure that there are no notes that are repeated. And so we're going to perform a series of changes to this original matrix. So the first sort of change is transposition, which is shifting all the notes in the sequence up or down by the same number of half steps. So when I say half steps, make sure that you know, because it can be confusing, that it's not by a 0.5, but it's actually by a full 1, because each 1 represents a half step in this 12-tone matrix representation. So we have this matrix, but then we shift every single element up by 2, so a 7 becomes a 9, 4 becomes a 2, and something that's important to note is to remember to use 0 to 11. So, for example, if we have the 10 and we add a 2, the number itself would be 12, but because we're only using 0 to 11, the 12 would be the same thing as a 0. Next up, we have inversion, which is switching every note in the scale to the other note that's equally close to the root note. For example, in an inversion, the third note in the scale would become the 9th, and the 7th note in the scale would become the 5th. An easy way to think about this is to think that 12 minus the note you already have is going to give you the new note. So for example, because 12 minus 7 is 5, we have 5 here, 12 minus 4 is 8, so we have 8 here, and that is how we got the rest of the matrix from this original matrix. Last but not least, we have retrograde, which is reversing the order of the notes. This is arguably pretty simple, so here you can see that if we went from 7, 4, 2, 1, blah, 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 we have, starting from the back, we have 11, 0, 10, 8, 11, 0, 10, 8, and then all the other notes are also in the reverse order. So by combining these shifts, composers can turn one sequence of notes in the chromatic scale, such as represented by this original matrix, into an extended and musically interesting piece of serial music.
So what we'll do now is we're going to create our own tone row, assigning the values 0 through 11 to the 12 notes in an octave. In our numbering system, our values are going to start with 0 being equal to A. There is no 12th value because after 11, the 12th value will also be A, but an octave higher. In between, every single note is a half step apart.
All of these are examples of techniques commonly used in serial music composition.
This is what the transposition of our melody sounds like when we move it up 2 half steps.
This is what the inversion of our matrix would sound like, which is when we replace each value with the number that you have to add to it to make it 12. So the difference between 12 and the existing number. And the only exception to that, as you will see, is that 0 stays 0. This is what it sounds like.
Our retrograde on our melody would be when you reverse the values inside of the matrix, therefore flipping the melody backwards, and it would sound like this.